Hi everybody, welcome to another video in differential equations, section 2.6. This is a very long section. In this section we learn three types of equation. The first one is homogeneous equation. Homogeneous equation is the equation in the form where we have the derivative equal to a function, and this function can be expressed as a function of y over x. Usually we let v equal to y over x. And if it is the case, then we say this equation is homogeneous. So once again, the function f of xy can be written as a function of y over x, or the function of v if v is y over x. If it is the case, then the equation is homogeneous. Now, if we write the equation in terms of dx and dy, I am dx and n dy, it is homogeneous if the sum of the degrees of each term in m and n are equal. So let's look at an example and see how it works. So we have this equation, and we'll show that this is a homogeneous equation. So we're going to use both of them. First, we just look at the function on the right hand side here. We have x squared minus y squared over 5xy. Right. What I do is I will split this in two. And then y squared over 5xy. Now, x squared cancel with an x at the bottom, y squared cancel with a y at the bottom. So when we do that, we will have, I will write 1 over 5 as a coefficient, and then x over y, and then minus, once again, that is 1 over 5. Cancel y with the y at the bottom, we have y over x. Now, you can put x over y and y over x. Now, if we let v equal y over x, then here we have v, and here x over y is the reciprocal of v. If v is y over x, so v to negative 1, we're going to flip, it's going to be x over y. So in that case, this equation, we can write them as, it can be written as x over y, which is v to negative 1, and minus 1 over 5 y over x is going to be v. So as you can see, we write the right hand side, the function in terms of v, where v is y over x. If that is the case, the equation is homogeneous. Right. So yes, if it is written in that form, then we certainly can do this. If we write that in the form of dx and dy, we certainly can show the same way too. So y prime, if we write as dy over dx, x squared minus y squared over 5xy. Now cross multiply 5xy dy equal to x squared minus y squared dx. Move both of them on the same side. Right. Now when we write the equation in the form with dx and dy, we see that the degree of each term. So we look at this one, we have x squared, degree is 2, y squared, degree is 2, and then the 5xy, x to the first, y to the first, multiply together, degree is 2. So all of them have degree 2. So that means it's homogeneous. So all the terms have degree 2. So that's why it is homogeneous. So either we show the equation is homogeneous in this form or in this form, it will be the same result, that the equation is homogeneous. Right, next, is this equation homogeneous? So we looked at this x to the first power y squared. So this one is degree 3 for that one, and here also degree 3, because x to the first, y to the second, 1 plus 2 is 3, y cubed, that's 3, x squared, and y to the first, 2 plus 1, also 3. But this term though, x to the fourth is degree 4. So it is not homogeneous because all of them don't have the same degree. So if it is written in this form, then we can see that it is not homogeneous. Right. Now, so we can determine if the equation is homogeneous. Now, how do we solve for it? Now, the solution. If the equation is homogeneous, that means we can write the right-hand side function as a function of v, where v is equal to y over x. Or we can write in this form, preferably in this form. Now, if that is the function y equal to v times x, we can take derivative, right? So if it is the case, then we take derivative. We can write y prime equal to, it's just a chain rule, product rule, v prime x plus x v prime. Yes, so we can write y prime as that. Or if we want to, we can write in other form, different form of product rule. So instead of write y prime, we can write derivative of everything with respect to x. By the way, that is completely wrong. Yes, so v prime x v prime x plus v x prime, right? Let me just write this. Y equal to vx. Y prime is v prime x plus vx prime. Derivative of x with respect to x is 1, so we just have plus v. Right? So let me just write more details. So y equal to vx. Now take derivative both sides with respect to x. And the product rule, derivative of the first term times the second plus the first term times derivative of the second. Derivative of x with respect to x is 1, so we just have derivative of v times x plus v, derivative of x is 1, so that's all we have, so we that. Or if we write in this form, and we cancel all the dx at the bottom, we can have dy equal to dv times x plus v times dx. Yes, so either the product rule in that form or the product rule in this form. Right, so that's the way we do the substitution. And when we do the substitution, the equation will turn into a separable equation. So the equation is homogeneous. Then we will let this, after we do this, it will turn into a separable equation. we see. Right, so first let's look at this example. Xy plus y squared plus x squared times dx minus x squared dy. Notice that xy degree 2, 1 plus 1, y squared degree 2, x squared degree 2, and x squared degree 2. So all of them have degree 2. So we say homogeneous of order 2, right? Then we will let v equal to y over x, or more precisely, we will let y equal to v times x. So that's where we start. And then the product rule is going to be v dx plus x dv, because that is the typo here. I will change this before I post this note online. So the product rule, v dx plus x dv, that one. If we have the derivative, then we can use that one. It doesn't matter. Right, so that product rule. Now we substitute everything into the equation. So where we have y, we're going to put vx, y squared, v squared, x squared, x squared, dx, same thing, xy, and dy is going to be v dx plus x dv. I'm going to substitute into that. So yeah, so substitute everything into the original equation, and then we simplify. When we simplify, we will divide both sides by x squared. When we do that, we have x squared here. This also x squared. This is x squared. This is x squared. So pretty much every single term have x squared in it. So we divide everything by x squared, and we have v squared plus 1 dx minus x squared cancel. We have this. Remove parentheses, turn to minus. And when we shuffle, there should be something to cancel. v dx, and we end up with v squared dx plus dx minus x dv. I move the x dv to the other side, and factor out the dx here. So I have v squared plus 1 dx times x dv. So this is not quite separable equation yet, but if I divide x on this side and divide v squared plus 1 on the other side, we have a separable equation, right? Move the x divide to the left and v squared plus 1 to the right. We end up with this separable equation. And integrate both sides. Integral of 1 over x is ln of absolute values of x plus c, and integral of 1 over 1 square of 1 plus x squared is tangent inverse of x plus c. So those are the integral for those two. And that integral of 1 over v squared plus 1 is tangent inverse of v. So we have that. I will take tangent on both sides. Tangent and the tangent inverse cancel out. We have just v. Right. So here from this equation, I will take tangent on both sides. And tangent inverse cancel out. We have tangent of ln absolute value of x plus c equal to v, and v is y over x. So I substitute that in here, and this is the equation that we have. Multiply the x over, and we have the solution here. So bottom line is the big scheme of things. When we have homogeneous equation, the first thing we do is let y equal to v times x, and the derivative follow is dy equal to v dx or x dv. substitute back into the equation, and we have that. Since this is the nature of the equation is separable equation, so I prefer to write this in terms of dy and dx, because dy and dx later on it will be turned into a separable equation. So that should be a better choice if we do that. Like I said, keep dx and dy instead of having the derivative. Right, but the idea of the homogeneous equation is we're going to use this substitution and the derivative from the product rule. Right, let's look at another example. So this equation we have dy over dx in this form. Right, like I said, the nature of it is a separable equation, so I prefer just write this in terms of dx and dy rather than take the whole thing as derivative. It will be better way to solve later on. By the way, this might be a long problem, so I will write in half a page and then continue on the other half. Right. Now first, of course, we can rewrite this as a function of x and x over y, y over x or x over y, it doesn't matter. But like I said, because when we do the substitution, it turns into a separable equation. So better to write that in terms of dy and then dx separate, meaning I will cross multiply it here. That will be better. So dy times that. So 3xy dy equal to x squared minus y squared dx. Of course, because of this term, it's not going to be separable. But we will do the substitution to make it homogeneous. Right. Degree 2, degree 2, degree 2. So this is homogeneous equation of degree 2. So we'll let y equal to vx. So y equal to vx, v times x, and consequently dy is v dx plus x dv. Right. And we will substitute this into the equation. Right. Try to write small because this looks like a long problem. Then we substitute into the equation. Yeah, so homogeneous equation, we're going to have this part. And now substitute 3x y, so 3x y is going to be vx, dy is going to be this, x squared, y squared is v squared x squared, oh that, right? So substitute into y and substitute into dx, in dy, sorry, that. Now multiply everything, multiply it all out. So that gives us 3x square v, and then multiply this with another v, so we have 3x square v times v, so 3x square v square dx plus, and multiply this, we have 3x square v multiply with one more x, that gives us 3x cubed v dv, and then this gives us x squared dx minus x squared v squared dx. Right, Now, because this is a homogeneous equation of order 2, so we should divide both sides by x to the order 2, so x squared. When we rewrite, we should be able to divide by x squared on both sides. Right. So that give us 3v squared dx plus 3x v dv dx minus x squared divided by x squared, so we just have minus v squared dx. Right, once again, homogeneous equation, do this substitution, and since it is homogeneous equation of order 2, we can divide both sides by x squared, x to the 2, or x squared. If this is of order 3, we should expect to have x cubed on both sides that we can divide by. Anyway, now, because when we do this, this should turn into a separable equation, so we try to keep dx and dv. So this is dx and dx. Move everything on this side, and the dv can move to the other side. So let's just move minus dx plus v squared dx. Move that to the other side, and move this to the other side. And so minus dx plus v squared dx. So move that to the other side, and then move the dx 3x v dv to the other side. Right, so we do that, we should have 3v squared plus v squared, so 3 plus 1, that's 4v squared dx minus dx. Right, so 3v squared plus v squared, that makes it 4 minus dx. Right, this side cancel out, and then the negative 3x v dv. Right, now next, factor out the dx, of course. We have 4v squared minus 1 dx, and then we have negative 3x v dv. Right, to get a separable equation, what we do is move the x to this side and move that to the other side. Right, so I divide by x on both sides. So I have 1 over x dx. So move the x to this side and move the 4v squared minus 1 to the other side. In that case, I still have negative 3v on the top. Just move the x down and move this down. Right, so when we do that, what we have here is a separable equation. Yeah, so homogeneous equation, when we do the substitution, when we rewrite it, it should be a separable equation. Right, Of course, when we solve this, integrate both sides. Right. So integrate both sides. So we start from there. So integrate both sides. When we do that, we will have integral of 1 over x dx equal to integral negative 3v 4v squared minus 1 dv. Yeah. So that equation, integrate both sides. So we have that. Right. Now, integrate both sides. The left hand side is ln of x, ln of absolute value of x plus c. That's easy. The right hand side, we need to use substitution. So use substitution. Right. I will let u be the denominator. Now focus on the integral. Let u be 4v squared minus 1. Take derivative. Du over dv is 8v, right? So we can solve for du is 8v dv, or dv is du over av, right? So we're going to substitute that into dv, and u is the denominator, right? The left hand side is easy, so I just keep 1 over x dx, because later on that's just ln of absolute value of x plus c. And now we have negative 3v 4v squared minus 1 is going to be u dv is du over av. Now the substitution, if we've done correctly, there will be just the integral in terms of the new variable. So the new variable is u. Right, so that's simply fine. And I will take the negative 3 and 8. I'll take the negative 3 outside the integral and the 8 outside the integral. So once again, I'll just write the integral 1 over x dx. That easy. We can do that anytime. And the negative 3 on the top, 8 at the bottom. And then we have integral. So that cancel out, left with just 1 over u du. Right. Now we can integrate both sides. Integral 1 over x is ln of absolute value of x plus c. And here we can write negative 3 over 8 ln of u. Yeah, we only need c on one side. I keep c on that side. Right? Now, so that will be ln of absolute value of x plus c, and u is 4v squared minus 1. And finally y is v times x. So v is y over x. So we use that, substitute in here. So the equation, so the solution is ln absolute value of x plus c equal to negative 3 over 8 ln of 4 times v square is y square over x square minus 1. If we want to, we can simplify just a little more, but with the ln, of course, we can raise to the e and cancel that out, but I'm going to just leave it like that. Right, let me zoom it out a little bit so we can see the whole problem. That better. Oops. Right, that. Right, so that's the whole problem there. So once again, homogeneous equation, we use this substitution, y equal to v times x, and with that we have dy is v dx and x dv. Once again, the nature of this, when we do the homogeneous equation, if it is done properly, it will turn into the separable equation. So we might as well just write the x and dy separately like this. So later on it will be a separable equation. Right, so substitution for y dy, and then we write. If it works out perfectly, we should be able to divide by x to the power, and whatever that power is the degree of the homogeneous equation. This is of degree 2, so we divide by x to the 2, or x squared. Right, move everything and try to separate them, x with dx and v with dv. We have this separable equation, and then we can just integrate both sides. We use substitution on the right hand side and integrate both sides, and that's what we have. So that is the homogeneous equation, the first part of the section. Now we go to the second part, and as mentioned before, this section has 3 parts. So the second part of it is the equation where we can use substitution. Right, so equation of the form derivative is equal to a function of combination of x and y. So if the right hand side is a function of combination of x and y, we will let that equal to z. Now since z is equal to ax plus by, we can take derivative on both sides, dz over dx. Derivative of that is going to be a plus b dy over dx, or we can solve for dy over dx. It's going to be 1 over b dz over dx minus a over b. So let me redo that part so we can see why. So once again, z is equal to ax plus by. Take derivative both sides with respect to x, meaning I'm going to put this in front of everything. A is a constant, so I can just write a and then d over dx, derivative of that of x, and then derivative of y with respect to x. Derivative of x with respect to x, derivative of x is 1, so this is 1. And if we try to solve for dy over dx, we minus 1 on both sides. And divide by b, and so we have 1 over b divided by b on both sides, and I forgot there's a here, right? That is a. So divide by b on both sides, and that's what we have. Where the calculator? Just a second, I just need to that's the calculator. Yeah, so we do that, we have dy with dx, because the problem we have is y prime, so that's why we write dy with dx and we substitute into that. And now the equation will be in terms of z is a function of x. Bottom line is the substitution is z equal to ax plus by, and then derivative is equal to that, and then we substitute into the equation, and we can write the equation in terms of the equation of z in terms of x, and that also a separable equation, and later on we can separate and we solve for it. So let's see how it works. So first, the equation derivative y prime equal to sine of x minus y. So usually if the equation in terms of substitution like this, it will be rather obvious. We can see right away that this should be z, and we take derivative z prime equal to 1 minus y prime, right? Derivative of everything with respect to x, and derivative of x with respect to x is 1. So now if it is the case, move the y prime over the z prime over, we have y prime is equal to 1 minus z prime. Substitute this back into y prime. We have this equation in terms of as a function of z in terms of x, and we rewrite this z prime is dz over dx, and write z prime dz over dx, move the dx over and move 1 minus sine z over, and if we do it correctly, we should have a separable equation. And we just integrate both sides. Now to integrate this, now the little trick of this is when we integrate this, we have to multiply top and bottom by the conjugate of 1 minus sine z, that's 1 plus sine z. So multiply that top and bottom. That is the trick to this. When we multiply that, the top will be 1 plus sine z, the bottom is 1 minus sine z times 1 plus sine z. Let's multiply this over here. So we multiply by the conjugate. 1 times 1 is 1 plus sine z minus sine z minus sine square. Sine cancel out. 1 minus sine square. And since sine square plus cosine square is equal to 1, so this is equal to cosine square, right? Pythagorean identity, cosine square plus sine square is equal to 1. So move the sine square over cosine square equal to 1 minus sine square. So that's why the denominator here is equal to cosine square. Right. And then we will split. Right. Skip a few steps because I don't want to take a lot of things to type, and also take a lot of space. So I will split. So once again, 1 minus sine z, 1 plus sine z at the bottom together is cosine square. So multiply this out. That gives us cosine square. Right. Now to integrate this, we will split 1 over cosine square plus sine z over cosine square. Right. And 1 over cosine square is secant. Sine over cosine is tangent. Let me rewrite one more step. I can write that as well, and then this I can write sine z over cosine, and 1 over cosine of that dz. Right, so we write 1 over cosine square as that, and sine z over cosine square we write sine over cosine and 1 over cosine. Sine over cosine is tangent 1 over cosine secant, so we have secant square secant tangent. Integral of secant square tangent, integral of secant tangent is secant, and that's what we have. And finally z is x minus y, so substitute back in, and that's what we have as the solution. So it's not that bad. Right? So that is that we will use this substitution. When we have that substitution, then we write y prime as a function of z prime, and then we rewrite that and we can solve the equation. So that's what we have. It's not that bad. Right, now take a look at our sample here. Solve this equation. Usually the equation, the type here is easy to recognize. If we have that z, then so notice that this is the function of x and y, not just any function of x and y. This is the combination, or we say the linear combination of x and y. So we have a constant times x and a constant times y. In that case, we use substitution. If this is x squared, y squared, don't do that. It's not going to work. It has to be a linear combination of x and y. Right. So now, of course, it should be obvious that we're going to let z equal to x plus y plus 2, right? So that's where we start with. This is using substitution, so we will let z equal to x plus y plus 2. Don't worry about the space. We have some space on the next page. If you bring this out, should have enough space to write the solution. So if that is the case, then we'll take derivative both sides. So z prime equal to x prime. Derivative of x with respect to x is 1. Derivative of y with respect to x is y prime. Derivative of 2 or any constant with respect to x is 0. So that's why when we have a constant here, it doesn't matter. It's going to be 0 anyway. And if we solve for y prime equal to z prime minus 1, right? So if that substitution and then this substitution, y prime equal to z prime minus 1, right? Substitute both of them into x plus y into this equation. So substitute into the equation. So substitute into original equation. When we do that, what do we have? dy over dx is going to be z squared, z prime minus 1. That dy over dx, or y prime. And then the right hand side, x plus y plus 2, that is z squared. Right. Now, as mentioned before, this should be a separable equation, right? So I move the 1 over z prime equal to z squared plus 1. Right. And we'll continue on the next page. Z prime is dz over dx. And z squared plus 1. Yeah. And we move the dx over, move the z squared plus 1 to this side. So we solve for, we should have the equation. By the way, this will not take as much space as we have here, so I don't need to divide the page in half. This dz, move the dx over, so dz equal to 1 plus z squared. I would prefer to write in that form. 1 plus z squared instead of z squared plus 1. move to the x over. That's what we have. And then divide by the 1 plus z squared on both sides. So we have that. And the other side just dx. I said if we do the substitution correctly, just like homogeneous equation, we will have a separable equation. Yeah, x and z. Now just integrate both sides. Right. Then we did one problem like this, right? Yeah. Integral 1 over 1 plus x squared dx is tangent inverse of x plus c. So this once again is the tangent inverse of z. So when we do that, we have tangent inverse of z equal to x plus c. Yeah, just integrate both sides. That's simple enough. Now, we can take tangent on both sides. So that cancel out, we have z. Tangent inverse, we have tangent of x. Tangent of x plus c. Right. We still need to rewrite this. Right, finally z, the equation, original equation does not have z. So that is x plus y plus 2. So z here have to revise x plus y plus 2. Yeah, original equation only have x and y. So we have tangent of x plus c. And if we solve for y, we have tangent of x plus c minus x minus 2. Right. Yeah. So that's what we have. So just like the homogeneous equation, we do the substitution. When we do the substitution, we have the new equation that we have. It will be a separable equation. So separable equation, we just separate the x and whatever the other variables. Integrate both sides. If possible, we can write y equal to. If we cannot do that, we can stop and just write the equation in that form. Yeah. So previously we have z, on previous example we have z equal to x minus y, so that at the end we put z is equal to x minus y. And we just leave the answer in this form. We're not going to solve for y. In this case, it's easy enough to solve for y, so we do that. If not, we can just leave the equation in this form. That's perfectly fine. Right, so that solution where we use substitution. This should be easy. It should be obvious that what is the substitution is going to be. Right, so one more example. This one. So if this is the equation, then we know that the substitution more likely is going to be z equal to x plus y, right? So that's where we start. Right, this will let z equal to x plus y. Right, notice the minus 1 is not part of the square root. The square root ends here. Does not have the minus 1, so that's all we have z. If the square root all over minus 1, then we will have x plus y minus 1 to be z, but this is not. So just leave that part out. Actually, that might turn out to be to simplify the problem a lot with the -1 here. Anyway, so z is that. We take derivative both sides with respect to x. So z prime equal to derivative of x with respect to x is 1 plus y prime. Right? Then we solve for y prime because that's what the original equation has. So we can say y prime equal to z prime minus 1. It's just minus 1 on both sides. And we substitute this into y prime and substitute this into x plus y. I substitute this into the original equation. So we have y prime, that's z prime minus 1, equal to square root x plus y is z, and then the minus 1 in this equation. Actually, the minus 1 and minus 1 here, as mentioned before, simplify on both sides, so that helps a lot. To cancel that out, we have z prime so we have z prime equal to square root of z. Right. Now, z prime, since like I said, when we do the substitution, it should turn into a separable equation. So we write z prime as dz over dx. Move the dx. And then move the square root of z down. Right, so we have that. And this is a separable equation. And we'll just integrate both sides. Integral 1 over square root of z, and we write this as z to negative 1/2. And integrate. Z to negative 1/2 integral is z to the 1/2. Increase the power by 1 and divide by the same thing. So negative 1/2 plus 1 is 1/2. And integral on the right hand side just x plus c. Right. And this is kind of like cross multiply, right? Multiply 1 to this and multiply 1/2 to that. So we have z to the 1/2 equal to 1/2 times x plus c. Yeah, cross multiply. Now, if we want to get rid of the 1/2, we can square both sides. Let me just continue over here. Just square both sides. So we have z squared. By the way, before we do that, the 1/2 x plus c, we can rewrite this as 1/2 times x plus 1/2 times c. Right? Now the reason we write like that, so 1/2 times c is still a constant. So in that case we can say z to the 1/2 equal to 1/2 x plus c. Because 1/2 of a constant is still a constant, we will write that as a constant. Right, now we square both sides. Z square is square both sides, square both sides, cancel the 1/2, so we just have z. And 1/2 x plus c. Yeah, square both sides, so the square here cancel with 1/2, and then there will be a square here. Finally, z, what was z? Oh, x plus y. So if x plus y equal to 1/2 x plus c square, and we can just minus x on the other side. If y equal to 1/2 x plus c square minus x. So that's what we have. Right. Let me zoom out so you can see the whole problem. Right. So once again, we use substitution. Substitution should be obvious as a linear combination of x and y. I just choose easy example here because usually the integral could be complicated. If this is like 5x and 2y, then we have a bunch of fractions that we have to deal with here. But if this is not the case, then it's not that bad. Then we let z equal to that, take derivative, solve for y prime, because that's what we need to substitute back in for y prime. And then when we do that, we should have a separable equation. Solve the separable equation. At the end, substitute back in for z. And that's what we have. So that is the second part of the equation where we use substitution. We let z equal to a linear combination of x and y. I said linear combination, but we can also have a plus a constant here. Actually, by the way, this is not a linear combination where there's the constant like that. But I said it can be a linear combination, and then it could add a constant to it too. Yeah. When that is the case, do the substitution, and then where there is a homogeneous equation or the substitution, if we do that correctly, we should have a separable equation. Separable equation should try to separate the x and whatever the variable is, dz or dv, and then integrate both sides. At the end, make sure that we write everything in terms of x and y. Right, the third part of it, of the section, is Bernoulli equation. So this is a little bit different than what we have as substitution and homogeneous equation. Let me zoom back in. Right, so what Bernoulli equation look like? So Bernoulli equation look like the first order equation, linear first order equation. If we don't have y to the n power here, this is the linear first order equation. So recognize that we have the linear first order equation except for the y to the n. So this is a linear first order equation or linear equation. So that is linear first order equation. The part that make it Bernoulli equation is y to the n. This part we make it to the Bernoulli equation. It's the y to the n. Right. So how do we write the solution? So Bernoulli equation. I did not put that in the note, but the solution is that we let v or z or whatever, but let's use v equal to y to the 1 minus n, and that's where we start. So n is the power of y. Now we do substitution. Let v be y to 1 minus n. We can take the derivative both sides. And this is the chain rule. Derivative of that is 1 minus n times y to the 1 minus n minus 1. So that is y minus n. And then dy or y prime. And then after that we'll solve for y prime. Right. Unlike the other form of like substitution, or we use the homogeneous equation, it will be easy to just remember that in Bernoulli equation we'll have this. Later on we will take care of that part, but we don't have to memorize that. We just need to know that we use this substitution. When we use this substitution, this will turn the Bernoulli equation will turn into the linear first order equation. So Bernoulli will turn into linear first order equation if we have v, if we do the substitution of v equal to 1 minus n. The rest will take care by itself. If we do it correctly on the calculus part correctly, we should have the linear first order equation. So just need to know that that is a substitution. With that substitution, Bernoulli equation will turn into linear first order equation. Right, so let's see how it works. Right, so let's solve this equation. Y prime minus 5y equal to minus 5 over 2x y cubed. So notice that in this equation, the y cubed here, make it a Bernoulli equation. Without it, it is just a linear first order equation. So this is Bernoulli equation. So that is the characteristic that stand out from the Bernoulli equation, is y to the n power on the right hand side. So with that, n is equal to 3, and the substitution is yv equal to y to the 1 minus n. 1 minus 3 is negative 2, so that's what we have. Now, we can write y equal to v to negative 1/2 as well. But let's just do that, and y equal to y to negative 2. Take the derivative on both sides, dv over dx, which is v prime, and derivative of y to negative 2 is negative 2, y to negative 3, and the chain rule, dy over dx. Yeah. So derivative by the chain rule, we take the derivative with respect to y, and then we have dy over dx. And now to solve for dy over dx, divide by negative 2 on this side, and divide by the y to negative 3 on the other side. So let me clarify that. Here we have dv over dx is negative 2, y to negative 3, dy over dx. What we need to solve for is dy over dx. So I divide by this to the other side. Right, divide by that to the other side, and y to negative 3 at the bottom move to the top. That's why it becomes negative 1/2 y cubed dv over dx dy over dx. Right. Now we substitute that in for dy over dx. Again, substitute that into the original equation. That is y prime and y. We don't need to substitute that in v to negative 1/2. Don't need to do that. Just leave the y here and keep the y cube here. Don't worry about that. Just leave it like that. Right. Now, next, since we did say that this equation would turn into the linear first order equation, right? So if it is linear first order equation, we have to divide both sides by that. So we just have dv over dx by itself, right? That is the linear first order equation. So we divide by negative 2 y to negative. Just keep it like that. Anyway, multiply both sides by that. So try to get rid of this term and multiply both sides by that. We end up with dv over dx. And multiply that into this. Negative 2 times negative 5 is 10. Y to negative 3 times y is y to negative 2. And then we have negative 2 to negative 2 cancel out. That gives 5. Y cubed and y negative 3 cancel out. That's 5x. Right? So again, we only substitute in for y prime. Only substitute into this. Leave the y alone. Leave that y alone. Don't do anything with that. Because if it works out perfectly, what we should have here is the y to negative 2, right? And that looks familiar. That is v. So don't need to substitute everything in for y. Just substitute in the y prime. If it works out perfectly, we will have v in that, and that is the linear first order equation. Right. So linear first order equation, although this looks simple, but when we do that, integrating factor e to the 10x, multiply both sides, so this is standard. That gives us this. The problem here is we have to integrate this, which is integration by parts. And when we do that, dot here, that integration by parts, we'll have this. And divide by e to the 10x on both sides, we have v equal to this. Yeah, divide e to the 10x on both sides, we have v is that. And finally, v is y to negative 2. And I solve for y. We'll raise both sides to the... Here we have y to negative 2 equal to that. Now if we raise both sides to the negative 1/2. Negative 1/2 times negative 2, that cancel out. Equals y. And then we have the right hand side to negative 1/2. Right, so that's that. Now I just clarify doing the integration by parts. So integration by parts is the integral of 5x e to the 10x dx. Right, integration by parts. Integral of u dv. Yeah, it's fine. Just keep u and v here, even though there's a v there too. But it's uv minus integral of v du. So that is integration by parts. And in integration by parts, what we let equal to u is in this order. So log inverse trigonometric function, algebraic, usually the polynomial, anything is in a trigonometric function, an exponential function. We let u equal in this order. Right. Now when we look at this, we have 5x, and then we have the other one. So whatever we let equal to u will be in priority. Do we have any log? No. Logarithmic function? There's no. Any inverse trig function? No. Algebraic function, and that is the 5x is the polynomial, or a is an algebraic expression, anything like polynomial. So that we let equal to u. Right. So we'll do u equal to 5x, and then the rest will have to be dv. In the formula we're going to have du, so we take derivative, du is going to be 5 dx, and dv, integrate, we have v equal to integral of e to the 10x dx is 1 over 10 e to the 10x plus c. And because integration by parts, we don't really need the plus c part. Right. By the way, I will send out the link of the review of integration, the video. I will send that on an email, you will see. Right, so integration by parts, uv minus integral v du. So u is 5x, v is this, minus v du. Right, and then simplify 5 and 10, so that gives us 1/2 x e to the 10x, and integral this 5 again, 1/2 times 1/10, so that will be 1 over 20. Yeah, I'm running out of space, but that'd be 1 over 20 e to the 10x. Yeah. 1 over 20. And of course, in this case, we will have the constant c on one of the side. And then to solve for v by itself, to get v by itself, we divide both sides by e to the 10x. Here. So when we do that, e to 10x cancel out, e to 10x cancel out, and c divided by e to the 10x is like e to the, it's multiplied by e to negative 10x, and that's what we have finally. V is y to negative 2, and y to negative 2, get y by itself. That's what we have. Right, so Bernoulli equation, if we let v equal to 1 minus n, we turn the Bernoulli equation into a linear first order equation. When we solve that, substitute back in terms of y, and that's what we do. Right, so here's some more examples. So this equation, once again, has to be in the standard form of linear first order equation. So this, because we have the y to the 4th attached to it, so this is the Bernoulli equation, because without that, this is a linear first order equation in standard form. So this is Bernoulli equation. Right. And in particular, n is equal to 4. And we need that. After that, Bernoulli equation, we will use the substitution. Let v equal to y to the 1 minus n. In this case, 1 minus n y minus 4, 1 minus 4, y to negative 3. And then we can take derivative, both sides. So v prime equal to, derivative of this is negative 3 y to negative 4, and then the chain rule say we have y prime. Right, now we will get y prime by itself, because after all we need to substitute into that. So we have v prime y prime, right? So y prime equal to v prime. I just divide this. Let's not worry too much about other things. Right. So we have derivative of y is equal to that. Right. Just divide by the whole thing down. Don't have to rewrite, move the y to negative 4 to the top. Just keep it like that. Perfectly. It will take care by itself. And this is the only thing we need to substitute into the equation. We not substitute this. So once again, v is equal to y to negative 3. Yeah. We not substitute this into the equation though. We do not need to solve for y in terms of v. That's all we need. It's a y prime. Right. Substitute y prime equal to 1 over negative 3 y to negative 4 v prime into the equation, just for y prime. Right. When we do that, the y prime becomes this. That's always need to substitute in. The other equation, part of the equation, will stay the same. Right. That's what we have. Now, this is supposed to turn into the linear first order equation. So if we multiply both sides to get rid of this, we have the linear first order equation. We should have the linear first order equation. So multiply both sides by the denominator. Right. So multiply that to everything. Since we have the whole page here, we just do that. So multiply that on both sides. Right. Of course, when we multiply that, the whole purpose of this is trying to get v prime by itself. Try to get to v prime, so that's obviously cancel out. So we have v prime minus a negative, that's a plus. Y to negative 4 times y, that's y to the negative 3. And that on the right hand side, negative 3, y to negative 4 and y to the 4th, that should cancel out. It's not always. Actually, it is always cancel out. Because what we do here, we're supposed to turn this into a linear first order equation. A linear first order equation has no y on the right hand side, right? So that's what it's supposed to be. That's supposed to cancel out. And furthermore, if it is done correctly, this will be equal to v. So we're supposed to have a linear first order equation right after this. And it is. So with v equal to y to negative 3, so we have the equation v prime plus 3v equal to negative 3 e to the 2x. And when we make the substitution for the Bernoulli equation, we have the linear first order equation. Yeah. If we do it correctly, the middle term here will turn into v, and there's no more y on the right hand side. Right, now linear first order equation, that should be simple. This is in the standard form, and p of x is equal to 3, so integration factor e to the integral of p of x, which is 3. So p of x is 3. So that is e to the 3x. Integral of 3 is 3x. And then multiply that both sides. So have e to the 3x. Now this is just linear equation that we saw before. Right. The left hand side will turn into a product rule. Will be just the integrating factor with y, but this case is v. Yeah. So the whole left hand side turn into a product rule of the integrating factor times the variable, the independent variable. The right hand side, that gives us negative 3 e to the 5x. Yeah, 2x plus 3x is 5x. When we multiply them, add the exponents. Right, now we just integrate both sides. Integrate, we undo the derivative. Right, that's easy. Is negative 3 e to the 5x over 5 plus c. Right. So let's rewrite this a little bit. E to the 3xv minus 3/5 e to the 5x plus c. Now we need to get v by itself, so divide e to the 3x on both sides. Yeah, I have enough space. Right, that cancels out. We have v equal to negative 3/5. When we divide, we subtract the exponents. 5x minus 3x is 2x. And move this to the top. right? And finally, the answer supposed to be y in it, right? We now don't have v. What was that? So we have v equal to y to negative 3. So we just substitute that in here. Yeah, we can leave the answer like this. Or if we want to, we can solve for y. And to do that, I will raise both sides to the 1/3. I mean negative 1/3. Because negative 1/3 times negative 3 cancel out, be just 1, right? Multiply the exponents. So y equal to negative 3 over 5 e to the 2x plus c e to the negative 3x of that to the negative 1/3. Right. So that's what we have. Right. So Bernoulli equation v equal to 1 minus n, and we just need to solve for the derivative y prime. Only need to substitute the derivative y prime. If it works out perfectly, we should have the linear first order equation. No more y or v on the right hand side, and the middle, that term have to be just v. If it works out perfectly. If you don't have that, there's something wrong there. And then we solve the linear first order equation. At the end, substitute back in for y and solve for y if we can. If not, just leave the equation like that. Right, so let's look at another example, Bernoulli equation. Right, so that is the equation, and what makes it a Bernoulli equation is, without this term, it is a linear first order equation. Let me just rewrite this. Y prime plus 1 over x y equal to x squared y prime. Y square, sorry. Once again, without the y square, that is a linear first order equation. So when we have the y square or y raised to any power to it, this will make it a Bernoulli equation. So if it is Bernoulli equation, I'll need to identify what is n, in this case 2. Right, now, and then Bernoulli equation based data, substitution v equal to y to the 1 minus n. N is 2, so we have y to the negative 1. 1 minus 2 is minus 1. Or we just say v equal to y to negative 1. Right. Now we will take the derivative of this. V prime. Derivative of this is take down the negative 1. Original power minus 1. Actually, I should do the proof of the Bernoulli equation, why this substitution will work. But this is a very long section already, so I just don't want to make it any longer. So derivative of this, v is v prime. Derivative y to negative 1 is negative y to negative 2. But in the chain rule, we have to take the derivative of y. Right. Now to solve for y prime, we just need to divide by that. We don't even need to simplify it. It will take care by itself. So y prime equal to 1 over negative y to negative 2 v prime. Yeah, just divide by y to negative 2 on both sides. y to negative 2 on both sides. We have y prime by itself, and 1 over that on the other side times b prime. So this is the substitution. The only thing that we need to substitute into the original equation. So substitute y prime equal to 1 over negative y to negative 2 v prime into the original equation. Right. The original equation is going to be this one, actually. So y prime is going to be this. Plus 1 over x y equal to x squared y squared. The rest of the equation will stay the same. We just substitute for the derivative. Right, now this is supposed to be a linear first order equation, so the first coefficient has to be 1. So I multiply both sides by the denominator. Yeah, so I will do that. Yeah, just multiply that on both sides. Right, negative y to negative 2, 1, 2, there. Right. Of course, that cancel out, we have v prime. This is 1 over x. Should be negative 1 over x. Right. Y to negative 2 times y. This by default, y to the first power. So when we multiply them, y to negative 2 times y to the first, add the power negative 2 plus 1 is negative 1. And on the right hand side, there should be no more y. Still negative though. Right, so that's what we have. Now, if it works out perfectly, this is supposed to be equal to v, right? And it is. So we're supposed to have just the equation in terms of v and x, linear first order. And then p of x is negative 1 over x. The integrating factor is e to the integral p to the x. Integrating factor. E to the integral negative 1 over x dx will be e to the negative ln of absolute values of x. So the negative can take it inside, and we write e to the ln of x, absolute value of x, to negative 1. E and ln cancel out, that is x to negative 1. If we go back to section 2.3, remember when we write like this, we can say it is x to negative 1, and absolute values can be written as just plus or minus 1. But we did say that the nature of the integrating factor is to be multiplied on both sides, so we don't really need the plus or minus. So we don't really need the plus or minus on both sides, because if we have plus or minus on both sides, that cancel out, so we don't really need that. So in the integrating factor, it's just x to negative 1. So just so in the integrating factor, if there's plus or minus, we can just ignore it. So let's do that and multiply both sides. Into this equation, of course. So x to negative 1 times v prime minus, and then x to negative 1 over x times v equal to negative x to negative 1 x to negative 2. I don't know where's that negative 2 come from, where this is just 2, right? Right, so even though the left hand side doesn't matter, remember the left hand side just a product rule. Don't even need to bother to simplify this. Don't even need to simplify this. It is just integrating factor times v. And I don't know why I write to negative 1. In fact, this should be derivative, right? I said the left hand side doesn't matter. It is the product rule. Derivative of integrating factor times v. That's much we know. So what's that? Right, as mentioned before, left hand side must be a product rule, and that's what we have. Right, right hand side, that's negative x negative 1 and x squared at the power negative 1 plus 2 is just x. Yeah, negative 1 plus 2 is 1, so just x. And integrate both sides. So we have x to negative 1 v integral of this is negative 1/2 x squared plus c, and multiply both sides by that. Yeah, have enough space. Multiply both sides by it. Actually, divide both sides. Yeah, see, we try to get rid of that. So that we have v equal to -1/2. When we subtract the power 2 minus -1, that is 3, and move that up, we have cx. I lie with run out of space. Right, v, finally, what is v? Y to -1. Substitute that in for v, and so we have -1/2 x cubed plus cx. Now if we raise both sides to the reciprocal power, so we have y equal to -1/2 x cubed plus cx to the -1. Yeah. So we raise both sides to the reciprocal power. -1 times 1 is 1, and that's just y. And to the -1 is the reciprocal power. Or we can write y equal to 1 over -1/2 x cubed plus cx. Sorry, just that under the denominator, 1 over -1/2 x cubed plus cx. Yeah. So, Bernoulli equation. It's just a linear first order equation, but we multiply by y to the n power at the n on the right hand side. So the solution is v to y to the 1 minus n, and we just solve for y prime. Only substitute that into the equation. If it works out perfectly, the linear first order equation, we have v there, and there will be no y on the right hand side. Linear first order equation, we just solve for that, and at the end substitute back in for v and solve for y. Right, so that is the solution. Right. So with that, I stop this section right here. This section once again has 3 parts: homogeneous equation, or we use substitution. Those two will reduce the equation into a separable equation. Bernoulli equation is the last part, where we make this substitution and we turn that into a linear first order equation. As always, I hope you find this video helpful. Thank you for watching.